All right, another method you learned in Math 252 to determine linear independence of functions was a method called Wronskian, using Wronskian method basically. So using Wronskian to determine linear independence of few functions. So let f1 to, let's say, fn be functions that are differentiable with from any order so f1 to fn are functions that are always differentiable and differentiable from second order and differentiable from third order, they're differentiable from any order, such as most functions that we are familiar with, for example, sine x, cos x, e to the x. So these are or polynomials, these are the functions that are differentiable from any order. Then we can define Wronskian of these functions f1 to fn as follows. So W of f1 to fn, we define it as determinant of f1 to fn, f1 prime to fn prime, and all the way to f1 n minus 1 derivative to fn n minus 1 derivative. And this is a function of x. Now, if W of f1 to fn is identically equal 0 for every x, then f1 to fn, are linearly dependent. If this determinant is identically zero, meaning that it's 0 for every x, then we can say that these functions are linearly dependent, and otherwise meaning that if W of f1 to fn is not equal to 0 for at least one value of x, then we can say that f1 to fn are linearly independent. I remember in the previous semester, there was a common mistake that many students thought that this W of f1 to fn must be non-zero for every x in order for functions to be linearly independent. That's not the case. If this determinant Wronskian is not 0 even for one value of x, then we can say that the functions are linearly independent, even if determinant is non-zero for one value of x. But if it's 0 for every x, if it's constant function 0, then they are linearly dependent. So let's look at an example. So let's say show that let's say e to the x and e to the 2x are linearly independent. So right now we have two functions which are differentiable from any order, e to the x and e to the 2x, both of them exponential functions. And we want to show that these two functions are linearly independent. Let's first do it with the definition of linear independence. So solution 1, using definition of linear independence. So let's say C1 e to the x plus C2 e to the 2x equals 0. When we say, see, this is a function, this is a function, this is a linear combination of two functions, which is a function itself. So when we say that a function equals 0, we mean that it's equal to 0 as a constant function, meaning that left-hand side is equal to 0 for every value of x. So when we say this is equal to 0, we mean it's identically equal to 0. So let this be equal 0, then I want to show that C1 and C2 must be both 0. Remember, if you want to show that few vectors are linearly independent, you have to assume that some linear combination is 0, and you have to be able to conclude that all coefficients must be 0. So here I have to be able to conclude that C1 and C2 must be both 0. So how can I do that? Well, this is true for every x. So now if I replace x with 0, then I will have C1 plus C2 equals 0. And if I use, let's say x equals 1, then I will have C1e plus C2e squared equals 0. And I can write this system. So this system can be written as this form. Basically, I can write it as 1 e squared times C1 C2 equals 0. So I wrote it in the matrix form. You remember how matrix multiplication works from linear algebra. If you want to multiply a matrix with vector, matrix multiplication is row by column. So you have to multiply first row by first column, then I'll have C1 plus C2 equals 0, and then second row by first column, it will give me C1e plus C2e squared equals 0 again. So this system, linear system, can be written in the matrix form this way. Now, I want you to recall from Math 252 that a linear system, a homogeneous linear system, let me say a homogeneous linear system, of the form ax equals 0 has only the trivial solution x equals 0 if and only if A is invertible and this occurs if and only if determinant A is not equal to 0. So these are three important equivalent conditions for invertibility of A. So A is invertible if and only if determinant of A is non-zero, and that happens if and only if this homogeneous system AX equals 0 has only the trivial solution x equals 0. Here A is n by n square matrix. Here we can say where A is a square matrix has only the trivial solution, because determinant is only defined for square matrices, also invertibility only for square matrices. So we assume that A is invertible. So we assume A is square. Now, if A is square, then AX equals 0 has only the trivial solution x equals 0, if and only if A is invertible, and that happens if and only if determinant A is non-zero. So now in this example, in example above, our matrix A is 1, 1, E squared. So determinant A will be E squared minus E, which is not 0. Determinant of 2 by 2 is like AD minus BC. This times this, 1 times E squared, which is E squared minus 1 times E, which is E. E squared minus E is non-zero. E is like 2.7 something, right? So E to power 2 will be definitely different than E itself. So E squared minus E is non-zero. And determinant A is non-zero, that means A is invertible, and therefore A times C1, C2 equals 0 has only the trivial solution. Trivial solution C1, C2 equals 0, which means that C1 and C2 are both 0. And that's exactly what we wanted to show. And that means e to the x and e to the 2x are linearly independent. So my x here in this example, see, this is my A and this is my x. AX equals 0. AX equals 0 has only the trivial solution x equals 0 if A is invertible. Here, we verify that A is invertible because determinant A is non-zero. So AX equals 0 has only the trivial solution x equals 0. What is x? X here is the vector C1, C2. So vector C1, C2 must be 0. And that means C1 and C2, both of them must be 0. And that's exactly what we wanted to show in order to show that these two vectors are linearly independent. If I want to show that these two are linearly independent, I have to assume that this linear combination is 0, and I have to be able to conclude that C1 and C2 must be both 0, and that's what we concluded here. Therefore, these two functions basically are linearly independent. So this was the solution without using Wronskian, only using the definition of linear independence. Now, solution 2, we can also do it with Wronskian. Using Wronskian, we want to show that these two functions are linearly independent using Wronskian this time. Okay, what is Wronskian of these two functions? So W of f1 and f2. Here, f1 of x equals e to the x. f2 of x equals e to the 2x. So W of f1 and f2 is equal to determinant of f1, f2, f1 prime, f2 prime. And that's going to be determinant of e to the x, e to the 2x. Derivative of e to the x is e to the x. Derivative of e to the 2x is 2e to the 2x. And this determinant will be 2e to the 3x minus e to the 3x. This is e to the 3x, which is not equal to 0 for, in fact, every value of x. But as we said, even if it's not 0, even for one value of x, that's enough for us in order to be able to conclude that the functions are linearly independent. So this is not equal to 0, let's say, for, say, x equals 0, because at x equals 0, e to the power 0 is 1, which is not 0. E to the power 3x will be 1, which is not 0. And therefore, since Wronskian is not 0 for at least one value of x, so we can say W of F1 and F2 is not 0 for at least one value of x. And that means F1 and F2 are linearly independent. All right, let's look at another example. So this example, we could do it with two different methods, using definition and using Wronskian. So another example that we already saw, that the functions were linearly dependent. If you remember, the functions were sine squared, cos squared, and 1. So we saw above that f1 of x equals sine squared x, f2 of x equals cos squared x, f3 of x equals 1 are linearly dependent. We can verify this using Wronskian. In the previous method, we didn't use Wronskian. We just used definition of linear independence. But if you use Wronskian, again, we get the same result. So what is W of F1 and F2 and F3 will be determinant F1, F2, F3, F1 prime, F2 prime, F3 prime, F1 double prime, F2 double prime, F3 double prime. So this is going to be determinant of F1 is sine squared, derivative sine squared, F2 cos squared, F3 is 1. So first row is just the function sine squared x, cos squared x, 1. Then we have the derivative of sine squared, which is 2 sine x cos x. And then we have derivative of cos squared, which is minus 2 sine x cos x. Derivative of 1 is 0. And then we have the next derivative, second derivative of sine squared, which is derivative of 2 sine x cos x. So 2 sine x cos x is sine 2x. If we use this fact that 2 sine x cos x is sine 2x, then we can easily differentiate. Derivative of sine 2x will be 2 cos 2x. And derivative of minus sine 2x is minus 2 cos 2x. Derivative of 0 again is 0. Now, if we expand along third column, so this is a determinant. We know that if you want to expand the determinant, we can expand along any row or any column. Now, in the third column, I already have 2 zeros. So of course, it's easier to expand along a third column. So let's expand along this column. Along this column. Then we get 1 times. So I have to delete this row and this column, and what will be left? This guy times this guy minus this guy times this guy. And there is no extra minus because this element is in the n3 first row, third column, and 3, 1, 3. 1 plus 3 is even. If 1 plus 3 is even, that means there is no extra minus in front. But if this was, for example, n3, 2, 3, 2 plus 3 is odd. So then I would have an extra minus in front. So there's no extra minus here. So 1 times, and then delete first row, third column. This 2 by 2 determinant will be left. And I just need to calculate it, which is this guy times this guy minus this guy times this guy. So it's going to be sine 2x times minus 2 cos 2x minus sine 2x times 2 cos 2x and so this is minus 2 sine 2x cos 2x. This is plus 2 sine 2x cos 2x. They cancel out, and then the answer will be 0 for every x, of course, for every value of x. Because no matter what x is, this term will cancel out with this term, and the result will be 0. So the answer is 0 for every value of x. So that means F1, F2, F3 are linearly independent and linearly dependent, because the Wronskian was 0 for every x. So F1, F2, F3 are linearly dependent. All right, another concept related to linear independence and linear combinations that you learned in Math 252 was basically basis, the concept of basis of a vector space. Basis, so a set, let's say V1 to Vn is called a basis. It's called the basis for the vector space V. If, first of all, this set V1 to Vn is linearly independent. So we need our vectors to be linearly independent if they want to form a basis. And moreover, so the linear independence is necessary, but not enough. And moreover, second condition, every element of V, element of vector space V, can be written as a linear combination of V1 to Vn. So you already know about the concept of linear combination. If every element of V can be written as linear combination of V1 to Vn, and also if V1 to Vn is linearly independent, if both these two conditions hold, then we call V1 to Vn a basis for the vector space V. The number of elements in included, the number of elements included in a basis for V is called the dimension of V, the dimension of V, denoted by dimension V. So dimension means the number of elements included in a basis for V. So you may ask, how about if I have, let's say, two different bases for a vector space V? Then dimension is defined as the number of elements in the first basis or number of elements in the second basis. Well, it can be shown, it can be proved that any two different bases, we could have two different bases, that's possible, but number of elements in those two bases will be exactly the same. So if you have two different bases, they will definitely have same number of elements. It's not possible to have two different bases with two different number of elements. You can have two different bases, but number of elements in those two bases will be exactly the same. So that's why dimension of the vector space is well defined in this sense, that if you have two different bases, they have same number of elements. Number of elements in any basis is called dimension of that vector space. So let's look at an example. Before doing an example, so it can be also shown that in a vector space, or let's say if V is a vector space with dimension n, then any set, any linearly independent set with n elements will form a basis for V. So if dimension is n, then any linearly independent set with n elements will automatically form a basis for V. In other words, if the number of elements in the set is the right number, meaning that it's the same number as dimension, then you don't need to check the second condition. Because if you want to use the definition, you have to check both conditions. But if you use this theorem, it will be more convenient because you can just check the number of elements in the set, compare it with the dimension. If they match, then you just need to check linear independence, which is the first condition. And then you can say that by this theorem, it will form a basis automatically. We don't need to check the second condition. So let me give you an example. Let's say show that this set, for example, let's say 1 and 2 and 5 and 8, let's say, forms a basis for V equals R2. So we know from Math 252 that dimension of Rn is n, right? So we know that dimension of R2 is 2. And this set has two elements. So see, the number of elements in this set matches with dimension of this vector space. This is 2, this is also 2. So if this was 3, for example, then the numbers would not match. But the number matches, right? And this is 2 and this is 2. Or if this was if you had two elements here, but this was, for example, R3, dimension of R3 is 3, and if you had two elements, again, the numbers would not have matched in that case. But right now, the number of elements in this set is 2, dimension of this vector space is also 2, the numbers match. So the only condition that we need to check is linear independence. If this set is linearly independent, because the numbers match, we can automatically conclude that the set is linear. The set is a basis. So we know this dimension of R2 is 2, and the number of elements in the set above is also 2. So by theorem above, we just need to check linear independence in order to verify that this set is a basis. So let's verify that these two vectors are linearly independent. So let me assume that C1 times the first vector plus C2 times the second vector is 0. So that means if I expand, C1 plus 5C2 equals 0. And 2C1 plus 8C2 equals 0. And in matrix form, I can write it as 1, 5, 2, 8 times C1, C2 equals 0. Again, see, I have AX equals 0. We just mentioned a few minutes ago that if you have a homogeneous linear system in the form AX equals 0, so that system has only the trivial solution X equals 0 if and only if A is invertible, which happens if and only if determinant A is non-zero. So now determinant A equals determinant 1, 5, 2, 8. And that's 8 minus 10, which is minus 2, and that's non-zero. So by theorem above, we can say that AX equals 0 has only the trivial solution X equals 0. So that means my X here is C1, C2 is 0, and that means C1 equals C2 equals 0. So I concluded that both C1 and C2 must be 0, and that means my vectors are linearly independent. 1 and 2 and 5 and 8 is linearly independent. Okay, so the numbers, because then this number was the number of elements the set was 2, dimension was also 2. We verified that the set is linearly independent, and then we use the theorem to conclude that it must be a basis for our vector space. Now, another important concept you learn in Math 252, and I want to give you a reminder, is linear transformations. Linear transformations is another important concept you learn in Math 252. So let's say V and W be vector spaces, and let T be a transformation, which means it's a function. It seems that my screen is freeze. Just once. To W be a transformation and transformation here means a function. So V and W are vector spaces, and in particular, they are sets. And we have a function basically from one set to another. So we are already familiar with the concept of function. In this sense, you know that here we have vector spaces. The function is called a transformation in this context. Then T is called linear if, first of all, T of CV is equal to C times T of V for every constant C and every V in V. So that's one condition. And the second condition is that T of V plus W must be equal to T of V plus T of W. And this must be valid again for every V and W in the vector space V. So if you have a transformation that satisfies both these conditions, meaning that if you multiply a constant by a vector, the constant can be taken out, and T of addition is addition of T's, then we will call that transformation linear. And one convention is that a linear transformation of the form T from V to V is called a linear operator. So linear operator is a special case of linear transformation where both V and W are the same vector spaces. So instead of V to W, here we have V to V. In that case, we still, of course, have a linear transformation, but it's also called a linear operator. If you have a transformation T from V to V, which is linear, then we have a linear transformation. And in that case, it's also called a linear operator. So let's look at an example. Let's say T from R2 to R. And let's say T of A and B, let's say equals A squared plus B squared. Then T is not linear. So consider this transformation from R2 to R. When we say from R2 to R, means domain is R2. So the input must be a vector in R2. Here A and B is a vector in R2. And codomain is R, so the output must be a real number. Now here A squared plus B squared is a real number. And so we have a transformation T from R2 to R. Now we want to see whether this is linear or not. So let's see whether it's linear or not based on the definition of linear transformation. So let's first check the first condition. First condition, let's say, for example, T of, let's say 5 times 1 and 2. This is T of 5 and 10. I just chose some random number here and random vector here, doesn't matter. So T of 5 times 1 and 2 is T of 5 and 10, which is 5 squared plus 10 squared, and that's 125. So what about, let's compare this with 5 times T of 1 and 2. 5 times T of 1 and 2 is equal to 5 times T of 1 and 2 is 1 squared plus 2 squared. And that's 5 times 5, which is 25. So we saw that T of T of 5 times 1 and 2 is not same as 5 times T of 1 and 2. T of 5 times 1 and 2 is not same as 5 times T of 1 and 2, and that means T is not linear. Because in order to have a linear transformation, both these conditions must hold. Both these conditions must hold, and each of them must be true for every vector or every constant. And this one for every vector and every constant, and this one for every two vectors, any two vectors. So even if that means even if one of the conditions fails for one constant and one vector, or for one pair of vectors, then the transformation will not be linear. Now another example, let's say T from let's say C to C, where C is the set of all differentiable functions. So let this be defined as follows. So let's say T of a function f is defined as let's say f prime of x. T of a function f, we define it as f prime of x. Then T is linear. It is a linear operator. So solution, or show that T is a linear operator. Now the solution, in order to verify that T is a linear operator, first of all, it's operator because it's from C to C, from one vector space to itself. And if I want to show that it's linear, I have to verify the two conditions mentioned in the definition of a linear transformation. So here we need to check the first condition, T of C times F. This is by the definition of T, CF derivative, and by derivative properties, I can write this one as C times F prime of X. T of CF is CF derivative, and CF derivative is C times derivative of F. And C times derivative of F means C times T of F. And then the second condition, T of F plus G. This is F plus G derivative, because T of any function is defined as derivative of that function. So T of F plus G is defined, will be, according to the definition of T, will be derivative of F plus G. And again, by derivative properties, derivative of F plus G is F prime of X plus G prime of X. And this is same as T of F plus T of G. F plus G derivative, we know that from math 113, we know it's F prime plus G prime. Now F prime is T of F and G prime is T of G. And this is true for any two functions F and G in C. And the previous property was valid for any constant C and any function F in C. So when you want to show that something is linear, you have to prove it in general. You have to check the conditions in general for any function or any vector, depending on the context. But if you want to show something is not linear, then you need to show that it fails for at least one example. So this is always true in mathematics, that, if you want to show that something is true, we have to prove it in general. But if you want to show that the property fails or is not true, you just need to show that it fails for one example. But if you want to prove something, you cannot prove by examples. So here, if you prove that these conditions, or check that these conditions hold for specific functions, then your proof is not in general and you have not checked the properties in general. So your proof will not be considered as a correct proof. So to prove in general, like here, I assume that F and G are two arbitrary functions, or here I assume F is an arbitrary function, C is an arbitrary constant. But if you want to show something it fails, just give one example. Here we give one example of a vector that, the first property failed. But here we want to show that something is linear, so we have to prove or check the properties in general for arbitrary cases. So that means T is a linear operator. Now, in a similar example, which I can leave it as exercise, let T from C to C be defined as follows. So let's say C2 to C2. And here C2 is the set of all functions that are twice differentiable. That are twice differentiable. So let's define T of a function y as y double prime plus P of x times y prime plus Q of x times y. And here P of x and Q of x are two fixed functions. And y is a function in C2. So C2, we assume that is the set of all functions that are twice differentiable. And I want to define a linear transformation from C2 to C2. How do I define it? Well, the domain is C2. So if I have an input in C2, input in C2 means an element in C2 means a function that is twice differentiable. I'm calling it y here. Then T of y means the output corresponding to y. I'm defining it as y double prime, which means second derivative of y plus p of xy prime plus q of xy. So this is a transformation from C2 to C2. And the exercise is that you are asked to show that this transformation is linear. We define as this, show that T as defined above is linear. So you want to show that T is linear, which means that you have to verify the two conditions we mentioned previously. T of Cy, you have to show that it's same as Ct of y. And T of, let's say, y1 plus y2 is T of y1 plus T of y2. So these are the two conditions that you have to check for arbitrary constant and arbitrary function for the first property and for two arbitrary functions for the second property. So once you complete the solution of this exercise, then we'll be ready for proving the theorem that we mentioned at the beginning of the class. So now let's go back to our context. So back to Math 230. So these were some basic review from Math 252, basic concepts. Now, if you remember, in the beginning of the class, we were trying to prove a theorem. This theorem was saying that suppose that y1 and y2 are the solutions for this differential equation for this ODE, and you want to show that any linear combination of the form C1 y1 plus C2 y2 will be also a solution for this ODE. So let me call this one theorem star. So now let's prove this property or this theorem. So proof of theorem star mentioned in the beginning of today's lecture. So the assumption in the theorem says that y1 and y2 are solutions for this equation, for this ODE, y double prime plus p of x times y prime plus q of x times y equals 0. Now I want to define a linear transformation here. So define T from C2 to C2 as follows. T of y, we want to define it as y double prime plus p of x times y prime plus q of x times y. Now exercise above, you showed that T is linear. So we also know that T of y1, how much is T of y1? We were assuming that y1 is a solution for this. Y1 is a solution for this means that if I replace y with y1, the equation will be satisfied. So if I calculate y1 double prime plus p of x times y1 prime plus q of x times y1, this will be 0. because y1 is a solution for this ODE. So similarly, T of y2 is 0. So what will be T of C1 y1? Now I want to show that C1 y1 plus C2 y2 is also a solution. The goal is to show that C1 y1 plus C2 y2 is also a solution. Now how much is T of C1 y1 plus C2 y2? So because T is linear, I can write this one as T of C1 y1 plus T of C2 y2. And T of C1 y1, again, because T is linear, I can write it as C1 T of y1 plus C2 T of y2. And T of y1, I already know it's 0. T of y2, I already know it's 0. So this guy is 0, this guy is 0. So this will be 0. So we show that T of C1 y1 plus T of C1 y1 plus T2 y2 is 0. T of C1 y1 plus C2 y2 is 0. And what does that mean? That means C1 y1 plus C2 y2 double prime plus P of x times C1 y1 plus C2 y2 prime plus Q of x times C1 y1 plus C2 y2 is 0. Because T of any function y is y double prime plus P of x y prime plus Q of x y. So T of C1 y1 plus C2 y2 will be, if you call it, for example, W or whatever you want, then this will be W prime plus P of x W prime plus Q of x times W. And we already showed that this is 0, so this is 0. And that means C1 y1 plus C2 y2 is a solution for this ODE, for the ODE y double prime plus P of x times y prime plus Q of x times y equals 0. So we showed that once we assume that y1 and y2 are solutions, then C1 y1 plus C2 y2 will be also a solution for this ODE. And C1 and C2 are constant here, so constants here. So in our solution, in our proof, we use the concept of linear transformations. But if you want to avoid, using this concept or this approach, you could still do that. You could still, if you look at this equation, you want to show that this equation is 0. And to do that, you could expand this, because this is a second derivative of this function. You could write the C1 y1 double second derivative plus C2 y2 second derivative. And then this one you could expand as well, P of x times C1 y1 prime plus C2 y2 prime. And similarly for this one. And then you can arrange the terms. You can arrange this term here with this term all together. And then if you arrange these three terms together, you can take C1 out. And you will see that what will be left inside will be 0, because y1 is a solution for this ODE. Similarly, you can arrange the second and fourth and sixth term together. And Again, those three terms, if you take C2 out, you will see what will be inside, what will be left will be 0 again, because Y2 is a solution, and then you will still have 0. So you could potentially avoid this, notation of T and linear transformation, but this proof is more conceptual. It uses the fact that T is a linear transformation, and combined with the fact that Y1 and Y2 are solutions, we could immediately conclude that C1 Y1 plus C2 Y2, T of C1 Y1 plus C2 Y2 is also 0. And because T is linear and T of Y1 and T of Y2 were 0. And once we know that T of this guy is 0, means this guy is a solution. Because if T of some function is 0, that means that function is a solution for our ODE here. All right, so this was the proof of this theorem. Okay, so far we have shown that we showed that if Y1 and Y2 are solutions, then C1 Y1 plus C2 Y2 is also a solution. But now the question is, can we say that any solution for our ODE, which was Y double prime plus P of X times Y prime plus Q of X times Y equals 0, is of the form C1 Y1 plus C2 Y2. So we know that C1 Y1 plus C2 Y2 will be a solution, but can we say any solution will be of this form? In other words, the solutions that we get this way by considering C1 Y1 plus C2 Y2, do they generate all solutions, or they just some parts of solution? We could have other solutions other than the form C1 Y1 plus C2 Y2. So we know that this is solution if Y1 and Y2 are solutions, but do they generate all the solutions? In other words, can we say any solution will be necessarily of this form? We can say that as long as Y1 and Y2 are linearly independent. So the answer is if Y1 and Y2 are linearly independent, then we can say that any solution will be of the form C1 Y1 plus C2 Y2. So if Y1 and Y2 are not linear independent, then this type of solution C1 Y1 plus C2 Y2 will not generate all the solutions. But if Y1 and Y2 are linearly independent, then this type of solution will generate all possible solutions of our ODE. So let me state this as a theorem. So let Y1 and Y2 be two linearly independent solutions of Y double prime plus P of X times Y prime plus Q of X times Y equals 0, then any solution of this ODE will be of the form C1 Y1 plus C2 Y2. And here C1 and C2 are constants. So let's look at an example. Let's say y double prime. Let's say find the general solution. Find the general solution of y double prime plus y double prime plus y equals 0. So first we need two solutions, y1 and y2. Once we have two solutions, y1 and y2, then we can write the general solution as C1, two solutions which are linearly independent. It's important that they are linearly independent. Once we find two solutions that are linearly independent, then we can write the general solution as C1, y1 plus C2, y2. So first, let's guess. For the moment, let's guess the solutions. Later, I'll tell you the recipe how to find the solutions. But for now, let's guess solutions. Let's guess two solutions for this ODE. Now, the first one, a function that I want to try, y1, let's consider it as sine x. Then the derivative of sine x is cos x. The second derivative of y1, which is the derivative of cos x, will be minus sine x. So that means y1 double prime plus y1 will be minus sine x plus sine x, which is 0. And similarly for y2, let's consider it as cos x, then y2 prime derivative of cos x is minus sine x. And the second derivative of y2, which is derivative of minus sine x, will be minus cos x. So y2 second derivative plus y2 will be 0. So we showed that y1 and y2 are solutions. y1 and y2 are solutions of y double prime plus y equals 0. And now if I can verify that these are linearly independent, then the theorem above will tell me that any solution of this ODE will be of the form C1 y1 plus C2 y2. Next, verify that y1 and y2 are linearly independent. How can I show that they are linearly independent? I can use the original definition of linear independence, like C1 y1 plus C2 y2 equals 0, and show that C1 and C2 must be both 0. Or I can use Wronskian. So W of y1, y2 is determinant y1, y2, y1 prime, y2 prime, and that's determinant sine x cos x minus cos x, sine x cos x, derivative of sine x is cos x, derivative of cos x is minus sine x, and then this is minus sine squared x minus cos squared x, which is minus 1, and that's non-zero. So that means y1 and y2 are linearly independent. So by theorem above, we can say that any solution of y double prime plus y equals 0 will be of the form C1 sine x plus C2 cos x. Here C1 and C2 are constants. So if the initial conditions are not given, then our general solution will include constants. In the case of first order, it included one constant. In the case of second order, as you can see, it includes two constants. But if the initial conditions are also given, then there will be unique solution as long as everything is continuous, all the functions are continuous. Then you will have unique solution and you can find the constants. And to find the constants, you can use the initial conditions. So that's for uniqueness. So existence and uniqueness. So the theorem says that, if or suppose that P of X P of X and Q of X are continuous functions. On an interval I. Let's say on an interval I, and the functions P of X, Q of X, and F of X as well. Let me write this theorem in the general case, and F of X are continuous function on some interval I, and let A belongs to I, and assume that A, B naught, and B1 are constants. Then we can say that the initial value problem, then the IVP y double prime plus P of X times Y prime plus Q of X times Y equals F of X with the initial conditions. The initial conditions Y of A equals B naught, Y prime of A equals B1 has exactly one solution defined on the interval I. So as long as the functions that we appear in our ODE are continuous functions, then we can say that we have, and as long as they're continuous function, and as long as we have two initial conditions, because we have a second order ODE here, because we have second order ODE, we need two initial conditions, and as long as all the functions appear, which are P of X, Q of X, and F of X are continuous, then we can say that our ODE will have a unique solution. So with two initial conditions, as long as everything is continuous, we have a unique solution. A unique solution if the initial condition, if these two initial conditions are not given, if only this ODE is given, then we can write the general solution, including two constants. But when can we find the constants and write it and find the unique solution, find just one function? The moment that we are given the two initial conditions. So the example above, so let's look at the example above. So solve y double prime plus y equals 0 with y of 0 equals y prime of 0 equals 1. So in example above, we saw that we saw that general solution will be of the form y equals C1 sine x plus C2 cos x. And to find C1 and C2, use the initial conditions. So y of 0 is C1 times 0 plus C2 times 1, which is supposed to be 1. That gives me C2 equals 1. And y prime of 0 will be, see, y prime will be what? Y prime will be C1 cos x minus C2 sine x. At 0, it will be C1 times 1 minus C2 times 0, and that's 1. That gives C1 equals 1 as well. So y equals sine x plus cos x. This is the unique solution for IVP above, initial value problem above. So y double prime plus y equals 0. If only this OD is given, no initial condition is given, which is what we had in the previous example, we could find a general solution, including two constants, C1 and C2. Once the two initial conditions are given, and because everything is continuous here, so the constants here are, the coefficients here are just constants, and constant functions are always continuous. So because everything is continuous, see, the coefficients must be continuous. These coefficients must be continuous in order to have a guarantee for unique solution. And here the coefficients are constants, and constant functions are always continuous. So coefficients are continuous, and we have two initial conditions. So the theorem above guarantees having a unique solution. How can you find that unique solution? First, we need to find the general solution, which included two constants, C1 and C2. And to find the constants, always use the initial conditions. We had two initial conditions with two unknowns, two unknown coefficients, C1 and C2, and we use them to find them. And it turned out that both of them must be 1. And if both of them must be 1, y was C1 sine x plus C2 cos x. Both of them are 1, so the solution will be sine x plus cos x. Okay, guys, so that's all for today. Thank you and see you next time.